Hi, I'm Jeff Groh, and this is Differential Equations, Lecture 11. We have a few loose ends to tie up in the topic of Laplace transforms. So I would like to begin by discussing the gamma function. The lowercase Greek letter gamma is expressed like this, and the uppercase like this. The gamma function that we're going to talk about is the one denoted by a capital gamma. And by definition, gamma of t is the integral from 0 to infinity of e to the minus x, x to the power t minus 1 dx. In understanding the gamma function, I need a lemma. And in particular, I would like to show that gamma of t plus 1 is t times gamma of t. To prove this, we write gamma of t plus 1, which by definition is the integral from 0 to infinity, e to the minus x, x to the t plus 1 minus 1, giving us x to the t. We're going to perform an integration by parts. So u is the part that you need to differentiate. That will be x to the t. And dv is everything else, including the differential. du is then t, x to the t minus 1 dx. And v is minus e to the minus x. I'll put this in a box to set it aside. The integral is then transformed as uv minus integral v du. uv is minus x to the t e to the minus x, minus integral v du. We have a minus that comes out and makes this a plus. The t can also come out, and we get e to the minus x, x to the to the power t minus 1 dx. Note that this part is gamma of t, so we have t times gamma of t here. The theorem will be proved if we can show that the first part is 0. However, you can see that as x goes to infinity, the exponential decay will beat this polynomial growth. We're assuming here that t is greater than 0, and we get 0. When you plug in x equals 0, you also get 0. And so we have the proof. We have also to show that gamma of 1 is equal to 1. In proving this, note that gamma of 1 is the integral from 0 to infinity of e to the minus x, x to the power 1 minus 1, which makes this just 1. It follows then that we get negative e to the minus x. As x goes to infinity, exponential decay will send this to 0. And then we subtract what we get when we plug in 0. When we plug in 0, we get negative e to the 0, which is negative 1, for a grand total of 1. And that's the proof. As another lemma, I would like to show that gamma of n plus 1 is equal to n factorial, where n is constrained to be elements of the sets of natural numbers. This limit demonstrates that the gamma function is a generalization of the factorial. In particular, the gamma function is surely defined on the natural numbers, but it's also defined for other numbers, rational numbers, irrational numbers, all kinds of numbers that the original factorial function is not defined for. The proof is by induction. But before launching into the proof by induction, let's verify this. Let's look at gamma of 2. According to our preceding lemma, this is equal to 1 times gamma of 1, and gamma of 1 is 1, and so we get 1, which is 1 factorial. Gamma of 3 should be 2 times gamma of 2. Well, we know that gamma of 2 is 1, so this is 2 times 1, and that is 2 factorial. One more time. Gamma of 4 should be 3 times gamma of 3, which is 3 times 2 times 1, or 3 factorial. So you can see that this is proceeding according to the statement of the lemma, but let's prove this by math induction. The n equals 1 case follows from the lemma. Math induction proceeds by making the induction hypothesis, whereby we assume gamma of n hat plus 1 equals n hat factorial for some n hat. Not for all, just somewhere. We want to show that gamma of n hat plus 2 is equal to n hat plus 1 factorial. To this end, we'll start with gamma of n hat plus 2, which, by the previous lemma, is n hat plus 1 times gamma of n hat plus 1. Now, we know by the induction hypothesis that gamma of n hat plus 1 is n hat factorial. And if you multiply n hat factorial by n hat plus 1, you get n hat plus 1 factorial. And that concludes the proof. Now, for one reason that we're doing this, we want to calculate the Laplace transform of t to the power r, where r is an element of the set of real numbers, let's say positive real numbers to begin with, because our notion of the gamma function we haven't shown is defined when the number is negative. According to our definition for the Laplace transform, this is the integral from 0 to infinity e to the minus st t to the power r dt. If you make a change of variables, x equals st, then dx will be s dt. We'll assume here that s is greater than 0. The integral becomes, as you can see, as if t is equal to 0, x is 0, and as t goes to infinity, x will go to infinity. You get e to the minus x, keeping in mind that t is equal to x divided by s. We get x divided by s to the power r, and what is more, dt is 1 over s dx. It follows then that we have 1 over s to the r plus 1 times the integral from 0 to infinity, e to the minus x, and I'm going to express this exponent in a special way. It's going to be r plus 1 minus 1. This gives us a gamma function, gamma of r plus 1, and we're divided by s to the r plus 1. We've proved the following fact. The Laplace transform of t to the power r is gamma of r plus 1 divided by s to the r plus 1. The gamma function is known as a special function, of which there are many in mathematics. Next, I would like to teach you about a new operation called convolution. The convolution of functions f and g, we want these functions to be defined, say, on 0 to infinity, is defined by f convolved with g of t is the integral from 0 to t f of t minus x g of x dx. This convolution operation has a lot of remarkable properties and applications in the study of both ordinary differential equations and partial differential equations. I refer you to the classic partial differential equations text by Evans for a lot of very amazing examples of how the convolution operation works. First, I would like to have a theorem. If f, g, and h are piecewise continuous on the interval 0 to infinity, then 1. F convolved with g is equal to g convolved with f. So there's a kind of a symmetry or a commutativity in this convolution operation. Second, f convolved with g plus h equals f convolved with g plus f convolved with h. So the convolution operation has a distributive law. Third, f convolved with g convolved with h is equal to f convolved with g convolved with h, which means that the convolution operation satisfies a sort of associative law. Note that the convolution operation is looking more and more like a type of product. And finally, f convolved with the zero function is the zero function. This last property is obvious from the definition of the convolution operation. If you replace g by the function that's zero everywhere, then the integrand will be zero everywhere, and hence this will follow. I'll put a little smiley face here to indicate that this property is obvious. We won't prove all of these properties, but we at least need to prove the first one. The second one is also obvious because if you replace g by g plus h, you can distribute the f and break the integral into two pieces. So the second property is also clearly true. But we at least need to prove the commutativity of the convolution operation. So let's write f convolved with g of t, which by definition is the integral from 0 to t f of t minus x g of x dx. Now, there's kind of an asymmetry in the way that f and g are represented inside of this integral, and so it is a little surprising that the convolution product is commutative. We'll make a substitution. We'll set u equal to t minus x. Now, keep in mind we're integrating with respect to x. So that means that du is -1 dx. How does the integral transform? The integral becomes, well, when x is 0, u is t. If x is t, u is 0. We'll get a minus from here, f of u, x is equal to t minus u. So we'll have t minus u du. We'll rewrite this integral by doing a couple things. First, we'll flip the order of integration from t to 0 to t, and that changes the sign to a plus. Let's also rewrite the order in which the integrand is written. The variable u is a kind of dummy variable. This is a definite integral. Whenever you integrate a definite integral, the variable that you're integrating on doesn't appear in the answer. It gets eliminated. So this is a dummy variable. We could now replace u by x if we wish. And this is then clearly g convolved with f of t, and the proof is over. So why are we doing convolutions now? Suppose that f and g are piecewise continuous on the interval 0 to infinity and of exponential order alpha for some alpha. Let's also suppose that big F is the Laplace transform of little f and big G is the Laplace transform of little g. Then it turns out that the Laplace transform of f convolved with g is big F times big G. Or in other words, the inverse Laplace transform of f of s times g of s is f convolved with g of t. i.e., if you see in the process of solving a differential equation using Laplace transforms, if you see the product of two things that you know the Laplace transform of, when it comes time to take the inverse Laplace transform, what you get is the convolution of the functions little f and little g. The proof proceeds by taking the Laplace transform of f convolved with g. Well, this involves two integrals. First, the integral from the Laplace transform, and that gives an e to the minus st, but then we have this f convolved with g. We can write that as the integral from 0 to infinity, e to the minus st, the integral from 0 to t, f of t minus x, g of x, dx, and then dt. So we have a double integral here. Notice that we can rewrite the second integral as the integral from 0 to infinity of 1 minus the step function that occurs at t, f of t minus x, g of x, dx, dt. Now, we can move this into the inner integral. We'll get the integral from 0 to infinity, integral from 0 to infinity of e to the minus st, 1 minus ut of x, f of t minus x, g of x, dx, dt. It is at this point that we see that we're integrating in the xt plane over the entire first quadrant, from 0 to infinity on both. We can reverse the order of integration and we'll still be integrating over that exact same first quadrant. The only thing that changes is the differentials at the very end. Now we're integrating with respect to t first, which allows us to move the g of x out of the integral to this spot here. In addition, I would like to analyze the function 1 minus ut of x. This is, by design, 1 if x is less than t but bigger than 0, and 0 if x is greater than t. Note that this is exactly the same function as ux of t. If t is greater than x, you get 1. If t is less than x, you get 0. It follows then that we can rewrite this integral as the integral from 0 to infinity g of x. If this is expressed as ux of t, we'll have the integral from 0 to infinity e to the minus st ux of t f of t minus x dt dx. Now, because I've written the integral up here, you can see that this function is 0 until t is greater than x. So, in other words, we may as well replace the lower limit of integration by x, since it's 0 until it gets there, and 1 thereafter. Now, we'll make a substitution. We'll set u equal to t minus x, in which case t is u plus x. And also, the integral here is with respect to t, du will be equal to dt. How does this transform the integral? If t is equal to x, u is 0. And as t goes to infinity, u goes to infinity. T gets replaced by u plus x. Here we have f of u du, all of that times dt. This factor can be broken up into e to the minus su, e to the minus sx. This part does not involve u, so it can be brought out of the integral to join g. We have then the integral from 0 to infinity e to the minus sx g of x. We have the integral from 0 to infinity e to the minus su f of u du, all times dx. This part is the Laplace transform of f. And since this depends only on s and not on x, it can be brought out of this other integral. It follows then that we get the Laplace transform of f, and this is the Laplace transform of g, and that completes the proof. Let's do a simple example. Suppose I'm looking at some simple harmonic oscillator, but I don't know exactly what form I would like the forcing term to take yet. Here's what I'll do. Let's also suppose that the initial data are not moving and not displaced. The Laplace transform yields s squared times big Y plus big Y equals, well, big G. I don't know what it is. I'll just express it as big G. We'll factor the big Y out and have s squared plus 1 equals big G. We'll divide the s squared plus 1 off, yielding big Y equals g of s times 1 over s squared plus 1. At this point, we see we have the product of two Laplace transforms. This is the Laplace transform of little g, and this is the Laplace transform of sine of t. It follows that when we take the inverse Laplace transform, the solution will be g convolved with the sine function. Once we've decided what the external forcing function is, we can just plug it into here and we'll have the solution. If we want to change our mind and use a different forcing function, we just replace it here. You can see how we've solved an entire class of initial value problems in one fell swoop. We've not actually calculated to this point any convolutions. I'll remedy that with this example. I want to calculate the inverse Laplace transform of 1 over s squared plus 1 quantity squared. 1 over s squared plus 1 by itself is the Laplace transform of sine. It follows that this will be the sine function convolved with the sine function of t. How do we calculate the convolution of the sine function with the sine function? Well, we integrate from 0 to t, sine of t minus x, sine of x, dx. There are a couple of ways of solving this particular integral. One would be to use a product to sum identity, but I'm betting most of you don't remember that. So instead, I'll simply use the difference of angle identity for sine. We'll have the integral from 0 to t times sine of t cosine of x minus sine of x cosine of t all times sine of x dx. We can break this into a couple integrals. On the first term, after we distribute the sine x, the sine of t doesn't depend upon x, so it can be moved out of the integral. We'll have here sine of x cosine of x dx. On the second term, it's the cosine of t that could be moved out. And here we'll have sine squared of x. On the first term, we kind of need a 2 here to complete the double angle identity for sine. This will be the sine of 2x now. Whereas on the second term, we need to use a half angle identity, 1/2, 1 minus cosine of 2x. This gives us 1/2 sine of t. The integral of sine is negative cosine, but we have to divide by the 2 here. We have minus 1/2 cosine of t. We'll end up with t, or rather x, minus sine of 2x over 2, evaluated from 0 to t. Plugging in t, this 1/2 can be moved out, this negative can be moved out. We'll have negative 1/4 sine of t. When we plug in t, then with the negative 1/2 removed, we'll have cosine of 2t minus cosine of 0, which is 1. Over here, when we plug in t, we'll get t minus sine of 2t divided by 2, and then when we plug in 0, we get 0. We need to simplify what remains. To do that, we'll need to apply the double angle identity for cosine, and also a double angle identity for sine. So we have negative 1/4 sine of t. There are 3 double angle identities for cosine to choose from. I choose 1 minus 2 sine squared of t. We have a minus 1 over here as well, so these will cancel. We have minus 1/2 cosine of t, t minus, now the double angle identity for sine is 2 sine of t cosine of t. We have the divided by 2 here, which goes away. This gives us a negative times negative is positive, 2 times a fourth is 1/2. Sine cubed of t, and that's all that's left over from this first term. On the second term, we have a minus 1/2 t cosine of t. We'll have a plus 1/2 sine of t cosine squared of t. We can simplify this last term by replacing cosine squared with 1 minus sine squared t. We'll have 1/2 sine cubed of t minus 1/2 t cosine of t. When we distribute, we'll get plus 1/2 sine of t minus 1/2 sine cubed of t. This first term and the last term cancel each other out. This finally gives sine convolved with sine as 1/2 sine of t minus 1/2 t cosine of t. As another example, I'd like to look at the initial value problem y prime equals 1 minus y convolved with e to the minus 2t, where y of 0 equals 0. Notice we're using a convolution in the statement of the initial value problem. Taking the Laplace transform on both sides, on the left-hand side we get s times big Y. On the right-hand side we get 1 over s minus. Now because of our theorem, we're going to get the when we do the Laplace transform of a convolution, we just get the product of the Laplace transforms. The Laplace transform of little y is big Y. The Laplace transform of e to the negative 2t is 1 over s plus 2. To solve this problem, we need to get all the y's on one side. So we'll have big Y times s plus 1 over s plus 2, still equal to 1 over s. To add these fractions, we need to have a common denominator. So I'll multiply the first factor, the first term, by s plus 2 over s plus 2. Still equals 1 over s. On the left-hand side now, we get big Y times s squared plus 2s plus 1 over the quantity s plus 2 equals 1 over s. Multiplying the s plus 2 over, we get an s plus 2 in the numerator over here, and this is going to be s plus 1 quantity squared. To complete the problem, all we have to do is do a partial fraction decomposition on the right-hand side, and then take the inverse Laplace transform. To do the partial fraction decomposition, we have to express this rational function as a over s plus b over s plus 1 plus c over s plus 1 squared. Clearing the denominators, we get s plus 2 is a times s plus 1 squared plus b times s plus 1 plus c times s. Collecting like terms on the right-hand side, we'll have an s squared times a, and s squared times b, and those are the only s squared terms. For the s terms, we'll have a 2as here, we'll have a plus bs, and then plus c. And now for the constant terms, there's only one, and that is plus a. Equating coefficients on each side, we find that a, the constant term on the right, is equal to 2, the constant term on the left. Also, note that a plus b is 0 because there is no s squared term on the left, and that then implies that b is minus 2. Finally, we have 2a plus b plus c equals the coefficient of s on the left, which is 1. We already know a, so that's 4. We know b, minus 2, plus c equals 1. 4 minus 2 is 2. If we shift this to the other side, we arrive at c is negative 1. We have y equals 2 divided by s minus 2 divided by s plus 1 minus 1 over s plus 1 squared. Before calculating an inverse Laplace transform, note that this is 2 over s minus 2 over s plus 1 plus the derivative with respect to s of 1 over s plus 1. The effect of this being a derivative, remember that the derivative of 1 over x is negative 1 over x squared. And so you can see how this must be true. The effect of the derivative, you'll recall, is a factor of minus t. Minus the derivative is t times the inverse Laplace transform of whatever this function is. So technically, we might want to do a minus 1 here and a minus here. Minus the derivative gives us t times. Taking the inverse Laplace transform now, y is going to be 2 minus 2 e to the minus t minus t e to the minus t, and that is the solution to the initial value problem. We have one more topic to cover, and I don't want to do too much with this, but I at least have to pay it some lip service, and that is Laplace transforms and linear systems. We haven't given a full treatment of linear systems yet, and that's one reason I don't want to go too much in depth on this now. But at least you need to see what it is that we're talking about. Suppose we have a linear system like this. We can re-express this in a matrix form. In particular, suppose that I write the vector x is x, y, and the matrix A is the matrix A, B, C, D, and one more thing, the vector valued function f is f1 of t, f2 of t. Then this system may simply be written dx dt is ax plus f of t. Some of you may be a little weak on matrix multiplication, so I want you to see this in more detail. A times x represents the matrix A times the vector valued function x. When you multiply matrices, you take a row and multiply it by a column. If I take the first row and multiply it by the first column, I get the entry in the first row, first column. We take these two and multiply them over, and then add the products, ax plus by. When we take the second row and multiply it by the first column, we get the entry in the second row, first column. That's going to be cx plus dy. So this represents this expression. We have this added on. We'll add on the f1 and the f2, and that'll be the derivative of the components over here, the derivative of x and the derivative of y. So you can see the equivalence of the linear system with this matrix equation. Just for sake of notation, recall that Newton's notation for the derivative with respect to time can be compactly written as just a dot. Dots represent derivatives with respect to time. In Newton's notation, this notation is due to Leibniz. Another fact you need to know is that when we take the Laplace transform of a matrix times a function, that's going to be the matrix times the Laplace transform of the function. I.e., if big X is the Laplace transform of this vector valued function little x, then when considering the initial value problem, x dot equals ax plus f of t, x of 0 equals x naught, taking the Laplace transform yields s times big X minus x naught equals a times big X plus f of s. To solve this, we need to get all the x's on one side and everything else on the other. We'll have s times big X minus a times big X equals x naught plus big F of s. We would like to factor this vector valued function big X on the left-hand side, but you cannot factor it out on the left because matrix multiplication is not commutative. What is more, you cannot subtract a scalar s and a matrix A. It's not even defined. What you need to do is you need to insert an identity matrix. The identity matrix is normally denoted by I, or sometimes with a subscript, depending upon how many rows and columns it has. In the case of a 2 by 2 case, the identity matrix is 1, 0, 0, 1. And that's true because if I take 1, 0, 0, 1 and multiply that by A, B, C, D, using the rules of regular matrix multiplication, inserting the identity matrix here allows us to factor the vector x out on the right. That's still equal to x naught plus f of s. To solve for x, we need to get rid of this expression here. This represents a matrix. It's an n by n matrix. You can't just divide matrices, that's not defined. What you can do is you can multiply by the inverse of the matrix, if the inverse exists. For those of you who have studied this topic before, S can't be an eigenvalue. We'll talk about eigenvalues later in the course. For those of you who already know about eigenvalues, S can't be an eigenvalue because if it is, then this matrix is not invertible by definition of eigenvalues. And so S will have to be larger than the largest eigenvalue of the matrix A. That's the hypothesis that guarantees the existence of an inverse on some unbounded interval for values of S. If that's the case, then the inverse does exist. We can multiply both sides by the inverse of this matrix on the left and finally obtain X is Si minus A inverse times X naught plus F of S. I said finally, but there's really one more step. To solve for the solution X, we need merely take the inverse Laplace transform. And this gives us a general solution to linear systems using Laplace transforms. As an example, consider the initial value problem. X dot is 3x plus 6y plus t y dot is 2x plus 2y plus 2t plus 1 with the initial conditions x of 0 is 1, y of 0 is 7. Function big F of s is calculated by taking the Laplace transform of the forcing function here. The Laplace transform of t is 1 over s squared, whereas the Laplace transform of 2t plus 1 is 2 over s squared plus 1 over s. Also, the vector x naught is 1, 7. It follows then that x naught plus f of s is 1 plus 1 over s squared, 7, plus 2 over s squared plus 1 over s. I'm going to rewrite this as 1 over s squared times s squared plus 1, 7s squared plus s plus 2. You can see if I distribute this, I'll get 1 plus 1 over s squared, I'll get 7, plus 1 over s, that's this term here, plus 2 over s squared, which is the middle term here. The next step in the solution process is to calculate Si minus A. I is the identity matrix, S times that will be S0, 0S, and A was the matrix 3, 6, 2, 2, the matrix of coefficients of x and y on the right-hand sides in the differential equation. This gives us S minus 3, minus 6, minus 2, and S minus 2. In our formula, the next step was to calculate Si minus A inverse. You'll recall that if I have a matrix A, B, C, D, its inverse is 1 over the determinant AD minus BC. You switch the diagonal elements and negate the off-diagonal elements. In this case, 1 over the determinant is 1 over s minus 3, s minus 2, and then subtract the product this way, that's minus 12. We then switch the diagonal elements, s minus 2, s minus 3, and change the sign on the off-diagonal elements. Notice that this quadratic can be replaced by s squared minus 5s, because you get negative 2s minus 3s is negative 5x. We'll have a plus 6 minus 12 yields minus 6. This can be factored as s minus 6, s plus 1. So this denominator is factored in this way. The very next step in the solution process is to calculate Si minus A inverse times x naught plus f of s. We have then to multiply 1 over this times this. I'm going to write this as 1 over s squared, s minus 6, s plus 1, times this matrix times this vector, which I'll write below. Doing this matrix multiplication, we'll leave this out front for the now. You can see that we'll have s minus 2 times s squared plus 1 plus 6 times 7s squared plus s plus 2. Multiplying these onto here. Next, we multiply these two. That's 2 times the quantity s squared plus 1 plus the quantity s minus 3 times 7s squared plus s plus 2. We'll simplify this just a bit more. You can see the only s cubed term you're going to get when distributing this is this one s cubed. We'll have a negative 2s squared here, but a plus 42s squared here, for a net of plus 40s squared. We'll have a 1s term here plus 6s. Gives us 7s, and now the constant terms negative 2 plus 12 is plus a net of 10. In the second row, the only s cubed term is here, 7s cubed. Now the squared terms. 2s squared minus 21 is a net of negative 19, plus another one is negative 18s squared. For the s terms, we'll get 2s minus 3s for a net of minus s. And now the constant terms, 2 minus 6 is minus 4. From here, we need to distribute this scalar onto each coordinate of this vector. Then, we need to perform a partial fraction decomposition on each coordinate. But I can do that for you. Performing the partial fraction decomposition, we obtain this expression, which stands for the Laplace transform of the solution. The only step left is to take the inverse Laplace transform on each side to obtain the solution to the initial value problem. Taking the inverse Laplace transform on each side is then very simple. Here we have 2/9 minus 5/3t plus 61/9 e to the 6t minus 6e to the minus t, negative 7/18, and then plus 2/3 t plus 61/18 e to the 6t, and then plus 4e to the minus t. And this is the solution to the initial value problem.